Good day everyone. Well, in this video we'll quickly look at the design of a single stage common emitter transistor amplifier using the potential divider approach. Now the circuit diagram is quickly shown. This is the circuit diagram for potential divider. You see R1, R2 are the potential divider that forms a potential divider across the base of this transistor. The transistor to be used is a BC548. BC548. Now we see three capacitors, C1, C2 and CE. C1 and C2 are both input and output coupling capacitor respectively, while the CE is a emitter bypass capacitor. Now before transistor begins to work, there is a need for proper biasing, that is setting the operating point. As we all know that transistors have three different operations, different operation region: the saturation region, the active region, and the cut-off region. At the cut-off region, this is the transistor is used as a switch. Then at the active region, we make use of transistor as an amplifier. So in order to confine the transistor operation to the active region, so that the transistor will not enter saturation region, then we need to properly bias the transistor. But after the biasing, once the AC signal is set, then the effect of RE needs to be neutralized, and that is why we have put the CE, that is a emitter bypass capacitor. When transistor is operating under AC influence, it behaves as a short circuit, and we know when you place a short circuit across any resistor, the effective resistance of that circuit becomes zero. So that is exactly what the bypass capacitor does in that place. So the output of this transistor will be fed to either a loudspeaker or an oscilloscope, where we can physically measure the gain of the transistor. So the apparatus, the transistor is BC548. We need resistor, we need voltage supply. Then the design task is to find the value of R1 and R2 and find the value of RE. We are given the value of RC to be 2.9 kilo ohm from the aim, say to design a single stage transistor amplifier of a given gain, given that gain equals to 4, RC equals to 2.7 kilo ohms. So that is where we are starting our design from. So from here, design task is finding R1, R2 and RE. Now we know from formula that voltage gain is equal to RC over RE. That is what equation 1 is showing us. From there, if you substitute RC, which is 2.7 kilo ohms, and the gain we are expecting, which is 4, we find the value of RE. So from there, R will give us 680. Then step 2 is to find the DC operating point. The DC operating point, now when you draw the load line of a transistor, the load line equation, when you draw the load line graph of a transistor, the midpoint, in order to have a stable operation, you set your DC operating point at the midpoint of the graph, which is equal to VCC over 2. VCC is 9 volt, which gives us the DC operating point, that is VCE at I equals to 0 to be 4.5 volt. So if you apply KVL to the collector section, that is VCC becomes VCC equals to ICRC plus VCE, the voltage that is dropped along the capacitor and emitter terminal. So that gives us a VCC equals to ICRC plus VCE. So if we substitute IC, if we make IC the subject of the formula in this equation that you are seeing here, we'll be able to find the value of IC. VCC is known to be 9 volt. VC is known to be 4.5, which is a VCE at a quotient point, that is at the point of at the operating point, 4.5. Then the RC is 2.7 kilo ohms. So to substitute everything, we get 1.7 milliamps as the current that is flowing in the collector. Then from there, we know that voltage across the emitter is equal to current of the emitter multiplied by resistance of the emitter, and we equally know that an ID in an ID transistor, IC is equivalent to IE, because the base current is extremely low. So in most cases, it is neglected to be equal to 0, at least for theoretical analysis sake. It is assumed to be equal to 0. So when you do that, you'll be able to get the value of VE to be 1.16156 volt. From there, now see the voltage that will be dropped across the base will be the VBE plus VE. The voltage that will be dropped across the base terminal is going to be VBE plus VE, which is a VBE is 0.6 for transistor, for silicon transistor, which is 0.6 plus 1.156 give us 1.756. Then we make use of equation 4, which is a beta equals to IC over IB. So IC is known, IB is known. IC is known, beta is unknown. We remember we assume it to be 0, but in practical it is not going to be 0. But for theoretical explanation, we only assume it to be 0. So no beta for this transistor is 100. That is, the current amplification factor is 100. So when you put these values together, you get your IB to be 0.017 milliamps. You can confirm the by calculation. Then from there, if you have gotten IB, now if you go to this circuit diagram, you say that I2 is equal to 10 IB. It's a rule of thumb that we must understand. Now the reason for this rule is simple. Let me see if I can quickly explain it. Now when IB is assumed to be very, very low because of the high resistance of the base. Now when you have two resistors in parallel, and one resistor is so high that it is almost 10 times the value of the second, then the equivalent resistance in that circuit becomes the higher resistance. The equivalent resistance in that circuit becomes the value of the lowest resistance, because current prefers to pass through a low resistance path. So in effect, when you have two resistors in parallel and one is so high that is as much as 10 times the second, then the actual resistance in that circuit becomes the lower resistance. That is it. So that is why we say I2 is going to be 10 IB. It's a rule of thumb that we must understand. So 10 multiplied by 0.017 gives us this. Then from there, if you have gotten the I2, we know the V2 is I2 R2. So from there, we can now use this value to get a R2, because VB is equal to VB is equal to VE. So if you put this value together, you get VB over I2, which is 1.756 over this, to get the value of R2. V2 is equal to VB rather. So finally we need to find the R1. So if you go to the circuit diagram, you see that I1 equals to I2 plus IB. If you apply Kirchhoff current law, I1 is equal to I2 plus IB, which is 0.17 plus 0.017. So I1 is 0.187 milliamps. So from there we can find the value of R1. R1 is what? VCC minus VB over I1, which is 9 minus this. So conclusively, we are able to find these values for R1, R2. R1 equals, we approximated it to 39 kilo ohms. R2 is 10 kilo ohms approximately. RA is 680, and RC is 2.7. So please take note of these values. These are the values we are going to substitute into this circuit. These are the values we are going to substitute into this circuit in order to get the desired gain of that transistor. So in the next video, we are going to quickly run the Pro Tools simulation and see whether we are able to get the desired value. That will be all for now. Thank you very much for watching.